The first thing I would like to mention to this class is we add one more thing to the references. So the first one was algebra by Artin. So this is the references. And this is still our main reference, okay? We are following Artin now, and we will go into Hoffman-Kuhns when we do dual spaces. So linear algebra by Hoffman and Kuhns. Okay. And a third one, it's a bilingual book. So the main all the math stuff is in English, but some fun explanations are in Bengali. Okay, but this is a fun reading. Okay. So linear algebra by Professor Arnab Chakraborty. Okay, so this is our main reference, and I can specifically tell you what we are covering from where. So from here we will do dual spaces and annihilators. From here we will particularly do the proof of Cayley-Hamilton. Okay, and many of you have asked me about how to proceed with the exercises. So for the class tests or for the mid-sem, end-sem, if you particularly do the exercises, the relevant exercises in Artin, that would suffice. From Hoffman-Kuhns, just do the exercises in dual spaces and annihilators, and I think this will be sometime in the second half of the course. Okay. So for the first part, just do the exercises. There are plenty of exercises in Artin. Do the relevant exercises. Okay. It's divided chapter-wise or section-wise even. Do those. And that is my suggestion for the mid-sem or end-sem or for the preparation for the class test, the quizzes. Okay. Well, let's now come back to what we have studied. The last few concepts that we have seen. Okay. One was linearly independent set. This we also saw in the previous class. And then there were spanning sets. And then there are finite dimensional vector spaces. And then there were bases. Okay. Oh, by the way, here one more thing I must mention is that about grading, my grading are generally absolute. Okay. So take the quizzes more seriously. Okay. So now let's come back here. So let's consider the simplest kind of example. Just 0. Is it a vector space? Okay. Very well. Is it finite dimensional? Okay. So all right, then can you give me a basis of this? Empty set. So you know this, right? Okay. So basis for this V, it's a convention actually, and you will soon understand why we are taking this convention. It is an empty set. Okay. When V is the 0 vector space, please write down your name. And somebody else also, please enter, who entered just, please write down your name as well. Okay. So basis for V is an empty set, and do you know why this is? Why we take this convention? Okay, it will be clear soon. Okay. Now, linearly independent set. Suppose you have a linearly independent set L, okay, and suppose you throw away some of the elements from that. Okay. Does it remain linearly independent? Okay, and suppose you have a spanning set. Suppose you append more elements to it. Does it still remain spanning? All right. Thank you. So now we are going to see what happens other way. That is, if you add elements to a linearly independent set, or if you discard elements from the spanning set. Okay. And that actually has a very nice analogy with a children's story. So note that basis is something lying between linearly independent sets and spanning sets, right? So we are now in this scenario. Wait a minute. It would be nice to describe the story with some pictures. Okay. Okay. So in a children's fiction, two wise men are fighting each other about origin of some species. Okay, this species. Yeah. Okay. So two wise men fought over the origin of this species. One thought, rats grew larger and larger, and thus pigs evolved. Okay. Yeah, very wise. Another thought that this is too small. Okay. Elephants grew smaller and smaller, and thus pig evolved. So that was the conviction of the second wise man. And for our basis, we are in kind of a similar situation. Okay, here we have basis. Here we have linearly independent sets. And here we have a spanning set. Okay. So for the origin of pigs, both of the wise men were wrong. But we'll see that in our case, for basis, both of the ideas are correct. Okay. We can increase a linearly independent set to a basis, or we can start with a spanning set. We can decrease it and get a basis as well. Okay. So which side should we start with? Elephant? Okay, sure. Let's wipe this part because we need some space on the board as well. Okay. So from elephant to pig. Okay. Here's a proposition. At first, it might seem like we are adding elements to spanning sets, but soon this will be relevant to reduction of a spanning set. Okay. So suppose S is a spanning set of the vector space V. Okay. And suppose V is some okay, and let small v be some element in V. Okay. then, well, actually we are going to basis. I mean, could you just remember what are the properties that a basis must satisfy? Linearly independent, order. Right, very good. So since we are talking about ordered sets, let's start with an ordered set already. Okay. So suppose S is an ordered spanning set. Okay. We could of course do away with this, but just to see that we are going from an ordered spanning set to a basis, this might be relevant because we'll throw away some element, but the ordering will remain, right? Remain until it's a empty set, and there it's also vacuously the ordering is. I mean, it's true that it's an ordered set because there are no elements. If you have two elements, then you talk about ordering. If there are no elements, then you can also call that an ordered set because it's a. I mean, whatever is the assumption of ordering, it's hypothetically. I mean, it's vacuously true, right? So now suppose S is an ordered set. You take an element V in V and define S dash as the span of. Not span. Excuse me. If you just append V with S, so S comma V, that is, well, there might be, I mean, if you look from the, with the eye of a computer scientist, there might be a problem with the number of brackets, but when we are writing S comma V, that is we are appending V with this, just think of we are listing all the elements in S, and then we are just appending V there, okay? So, yeah, and since we said that we'll be considering only finitely generated vector spaces henceforth, you may also assume that S is finite, okay? So S is a finite ordered spanning set of the vector space V, okay? And S dash is this. Now, so S dash is defined to be this. Then we have span of S dash equal to span of S if and only if V is in the span of S. And the proof is going to be rather simple. So, yeah, it would be better if we see the proof from one of you. So maybe you assume this V in span S. What can you say about the span of S dash then? Yes, Shairam? Yeah? Yes? Right, okay. So we shouldn't take a spanning set, we just take a finite. Okay, yeah, sure. Thanks a lot, Sairam. In this one, we are not considering, we should not consider a spanning set yet. This is actually a lemma which will help us reduce the elephant to the pig. But in this particular case, we should not assume this. We just take S to be some finite ordered set. Okay. Thank you. S to be let S S is a finite ordered set. Okay. And this proposition is remains true even if it is not ordered, even if it is not finite. But we will apply it to this case. So let's go with this assumption. Okay. This proposition is more generally true. That is, S be whatever set and V be whatever vector in V. Okay. Then this is true. Thank you, Shairam. So, yeah. Now suppose we start with this. V is in spanning set. Okay. What can we say about V is in the span of the set S. Okay. What can we say about the span of S dash? What? Yeah. Right, because that V in span of S. V is in the span of S. Exactly. So V means it is a linear combination of the elements of S. Okay. Now, this one, span of S dash, means that it's a linear combination of the elements in S dash. So it's a linear combination of the elements in S and V. But V itself is an element, is a linear combination of the elements in S. Okay. So therefore, every element here is a linear combination of the elements in S. Okay. Is the explanation clear to all of you? Otherwise, you may raise hands and we can explain it again if any of you are falling back from there. Okay, that's great. Okay, so now this way implication is trivial from the definition of span. Okay. As we saw, trivial from the definition of span. All right. Now the other way. So we showed that V in span S implies that these two spans are equal. Well, now suppose the spans are unequal. What does it mean? So suppose span S dash is not equal to span of S. What can you say about V then? Of course, yes. Okay. So if and also the other way, I mean, if span S dash is equal to this, that since V is an element here, it should belong there. Okay. So basically the proof is rather simple, right? Follows directly from the definition of span. Okay. So if span S equal to span S dash, V is in span S. Okay. And the other way, sorry, earlier we did this way, right? That is V in span S, that means this, and this one was this, right? I mean, if span S is not equal to this, V is not in the span of S, and if they are equal, since V belongs here, V should belong to span S, right? So this is rather simple. Okay. Now suppose we start with such a set, a finite order set, which is spanning the vector space V. Okay. We want to reduce it to a basis. Can I wipe that part out? Thank you. Okay, so here's another proposition. Let S be a finite ordered spanning set of vector space V. Then S contains, well, yeah, fine. Then S contains a basis of V. Okay. How do you go about proving this? Yes. If it cannot contain, right. Yes. Exactly. Yeah. Yeah. Exactly. To reduce vectors, and it still spans the entire thing. Okay. All right. Your name is Manas. Thank you, Manas. So Sairam, is the argument clear? So thank you, Manas. So we proceed indeed in this manner. So if S is linearly independent, then S itself is a basis. If not, okay, at first let's assume that S is, if not, then S, which we assume to be this set V1, V2, dot dot dot, say Vn, must have then the elements in S, sorry, then the elements in S must have a non-trivial linear relation. Okay. So, non-trivial linear relation means that you have a linear combination C1 V1 dot dot dot, C1 V1 plus C2 V2 dot dot dot, Cn Vn, which is equal to 0, and not all the coefficients are 0. Okay. So, we need the middle board. Okay. So, let C1 V1 plus dot Cn Vn equal to 0 be such that not all the Ci's are 0. Okay. So, you may assume that one of the Ci's is non-zero. Okay. Then we take that particular summand on the other side. Okay. So, we have then minus Ci Vi equal to C1 V1 plus C2 V2 plus dot 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 plus Ci minus 1 Vi minus 1 plus Ci plus 1 Vi plus 1 plus dot 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 plus Cn Vn. So, you have taken this ith part outside and on the other side. Okay. All right. Now, remember that this is not equal to 0. So, you are allowed to divide by this. We are in a field. Okay. So, in particular, you are allowed to multiply with its inverse. Okay. Vi is minus C1 by Ci minus C2 by Ci minus dot 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 minus Cn by Ci. Sorry. C1 by Ci V1 minus C2 by Ci V2 minus etc. minus Cn by Ci Vn. Okay. So, what does it mean? Vi is a linear combination of the rest of the vectors in S. Okay. So, that is, this is inside the span of V1, V2 dot dot dot, Vi minus 1, Vi plus 1 dot 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 Vn. Okay. Okay. That is what you get after removing I from S. Okay. So, that means since Vi is in this span, now we apply this one, replacing this V with Vi. So, V is in the span if and only if these two spans are the same. So, the span of the thing with, so span of this thing with Vi and span of the thing without Vi. So, this is if and only if span of V1, V2 dot 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 Vn with all the things is equal to the span of V1, V2 dot 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 Vi minus 1, Vi plus 1 dot 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 Vn. Okay. So, these two spans are giving you the same space. Okay. And since it was a span of the entire space V, that means this one is also a generating set, a spanning set for the entire set V. Okay. And If this is a linearly independent set, we are done. If not, we can repeat the process. We can throw away another element from here, okay? And we may keep on going till we reach some, what is that? Wake up alarm for someone? So yeah, so till we reach the, till we reach a linearly independent set, we can continue the process, and yeah, so thus we can reduce the elephant to the pig, okay? That is the generating set to a basis. Okay. Now, one thing may happen, you keep on reducing it, and well, suppose you are in a situation where you have to throw away the last element. Can that situation occur? Exactly. If it is a 0 vector space, then even the last one you should throw away, right? Okay. And then what you are ending up with? The empty space. That's why we take the empty space as the basis of the 0 vector space. Okay. Yeah. Which part? Okay. Okay, so what vectors could be a basis for the empty set? Give me an example of a generating set for the space 0. Just take 0. Very good. Is 0 a linearly independent set? No. So what does the process say? If it is not linearly independent, what do you do? It's just a convention, as I mentioned. That is, we take the convention that the span of the empty set is 0. Okay.
Why 0?
Because only the other option that you may have, if V is equal to 0, you just said, right, that if you want to take a generating set, which one should you take? You want to take a generating set of this. Which one? Give me a generating set. 0. Yes. Is this set independent? Can you call it a basis? You cannot call it a basis, and that's why you must throw away 0. And that's why we take that as a convention that the empty set is a basis of the 0 vector space.
You're not taking this as basis because it is not a linearly independent set.
Yes.
So the span of the basis is the vector space.
Right.
So but the span of empty set is not that.
Yes, so that is the convention. So if you are saying that this is a basis of this vector space, then that implies that you are taking the convention that span of the empty set is the 0 vector. So you just take that as a convention, okay? Because there are no other option of a basis of the 0 vector space. Yes? Why this is not linearly independent, you mean? Okay, so what does linear independence mean? What is the definition? If a linear relation of the vectors you are considering in the linearly independent set is 0, then all the the only possible linear relation among a linearly independent set is that all the coefficients are 0, right? Now you take this as your set, take any coefficient that is giving you 0, right? Yes.
Why are you not saying that the 0 vector space has no basis?
That could also be a convention. On the other hand, then this algorithm you have to, so this is an algorithm of reducing the generating set to a basis. Okay, but this algorithm fails then, because you have a generating set 0, okay, and then if you throw away the element here which is linearly dependent, then you are ending up with the empty set. So this convention is actually making the proof work. So That is a degenerate case, but nevertheless, if you take this convention in that degenerate case, the proof then works for all vector spaces. Okay. Yes, Munir. Other singletons? Is there any other singleton vector space? You need 0 there, right? Yes. 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 Yes, but C1 need not be 0, right? Because you are multiplying with the 0 vector. So you can take C1 any element in the field. Yeah. All right. So we learned how to reduce the generating set or the spanning set to a basis with, I mean, only the thing that you must assume is that this convention, okay, for the entire proof to work perfectly for any vector space. Now we do the opposite. That is, we see how the basis grows from the linearly independent set, how the mouse grows into the pig. Okay. Yes. Why a vector space? A finite dimensional vector space, that is we are working with. Yes. And why does it have a basis? Okay. What does a finite dimensional vector space mean? Tell me the definition. Yeah. It follows from the definition, right? A finite dimensional vector space means that you have a finite generating set. You start with a finite generating set, and you get a basis. So it's not cyclic. It was defined to be a finite. A finite dimensional vector space is defined to be a vector space with a finite generating set. If you have a finite generating set, the space must have a basis. I mean, it's not only a finite generating set. The set should also. I mean, you should have a set sitting inside that finite generating set of elements which are linearly independent. Last time, Snowman gave an example of an infinite basis of a vector space, right? That is, take the set of all polynomials, and then this one, 1 x square dot dot dot. This gives a basis of the set of polynomials. Does it give a basis for the formal power series? That is, if you just write things like summation ai xi, I running from say 0 to infinity, without caring whether this is converging or diverging, just formal power series. Okay, is this set a basis for this one? What do you think? How many things? Yes, please raise your hands. High up. And how many things no? How many think no? Okay, people who are thinking no, people who are thinking yes, that's a, I mean, I see that we wrote it in this manner. So for yes, there's a reason. For no, what is the reason? If you, we are not talking about polynomials, we are talking about the space of these ones, the formal linear combinations of this exercise. Okay. And that we are not talking about convergence or divergence. We are just taking all such series. What? It's a basis. All of you think that it's a basis then, or no? Some of you raised hand and said that it is not a basis. So is there any other reason of not calling it a basis? Very good. So that is for a basis or a spanning set, you are supposed to take only finite linear combinations. Okay. Here you cannot. I mean, you cannot take any finite linear combination of that and get a power series, an infinite power series. in fact, if you take the set of sequences, set of all sequences, okay, and then take this sequence 0, okay, 1, 0, dot 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 dot, and 0, 1, dot 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 dot, and so on. Okay. And then, if I mean, this looks like the standard basis, right? That is, you are taking 1 at one point and 0 at everywhere else. So apparently, it looks like that this should be a basis of the space of all sequences over whatever field you are talking about. Okay. But it's not, because bases are defined to be finite linear combinations. Okay. So now the opposite construction, that is from linearly. So now we go from linearly independent sets to bases. Okay. So here's another proposition. Okay. So let L be a linearly independent set in a vector space V. Okay. And let V be some element in V. Okay. Then, okay, and let's define let L dash be this. Okay. When we are writing this, we should also take an ordered linearly independent set, right? Because we are just appending one element. Okay. So let L be an ordered linearly independent set in a vector space V, and we are defining L dash to be L and L appended with V. We are increasing our set. Okay. Then L prime remains linearly independent if and only if V is inside the V is not inside the span of L. Okay. And the proof is rather simple. Well, we do not prove this equivalence, we prove its contrapositive. Okay. That is, this is if and only if V in span L would be equivalent to saying that L prime is linearly dependent. Okay. And this is quite simple. It's kind of the same argument that we used here. Let's just for the sake of completeness, let's write it once more clearly. Okay. So proof, we started the proof there as well. Okay. So suppose it is linearly dependent. At first, give the names to the elements in L. So suppose L is this set, okay, and then then we have already defined what L dash is. Okay. So if L dash, which is equal to V1 dot 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 Vn comma V, is linearly dependent, that would mean that there exists a non-trivial relation, non-trivial linear relation of the form C1 V1 plus dot 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 plus Cn Vn plus Cn plus 1 V equal to 0. Okay. Now, is it possible in this non-trivial relation? Okay, non-trivial just means that such that not all the Ci's are 0. Okay. Now, is it possible that the last one is 0? Something else is non-zero, but the last one is 0. Is it possible? Why not? Yes, right. So, if this is equal to 0, and if this relation then C1 V1 plus Cn Vn equal to 0, if there exists a non-trivial relation like that, that would mean that this V1 to Vn are not linearly independent. But we started with the assumption that these are linearly independent, right? So, a non-trivial linear relation among this, that is, if L dash is linearly dependent, that gives a non-trivial linear relation, and that would imply that this is not equal to 0. Only this can be not equal to 0. Okay. In such a thing. Okay. Well, not only this can be not equal to 0, but if at least, I mean, one of the elements is non-zero and everything else is 0, it should not be that. Okay. So, that would imply that again we can take this to the other side, divide by Cn plus 1, okay, and get that V is equal to minus C1 by Cn plus 1 V1 minus C2 by Cn plus 1 V2 dot 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 minus Cn by Cn plus 1 Vn. Okay. That is V, since this is not equal to 0, we get that V, I mean, we can divide by it, that is, we can multiply with its inverse, and this belongs to then the span of L. Okay. So, we got that if L dash is linearly dependent, V is in the span of L. Now, the opposite, that is trivial, right? If V is in the span of L, that means you can represent V as a linear combination of V1 to Vn. Okay. Take that to the, I mean, take V to the right hand side then, and you get some linear relation among V and V1 to Vn. Okay. So, the opposite is trivial. On the other hand, if V is in span L, that would imply that, well, this is if and only V is equal to C1 V1 plus dot dot plus Cn Vn for some Ci in the field on which the vector space F V is defined. Okay. And that would imply that C1 V1 plus dot 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 plus Cn Vn minus V is equal to 0, a linear relation. Okay. That is, L dash is linearly dependent. Okay. And that is what we wanted to prove. Okay. So, you start with a linearly independent set, and then you add one element to it. If this is inside the span of L, this new set is a linearly independent set, otherwise it is a linearly dependent set. So, how should we now go from a linearly independent set to a basis? At first, you must have a finite dimensional vector space, and then, so here is the proposition. Yes. Which one? in the V. Yes. So what happens if it is 0? What was the proposition? What we are trying to show, that L prime remains linearly independent or not. Now, if V is equal to 0, you can immediately say something. L prime is linearly dependent because it has some element which cannot be linearly independent. Okay, so L prime is linearly dependent by definition then, and of course the hypothesis of the proposition is satisfied because 0 lies in the span of any vectors, right? A span is a subspace that you have already seen. Okay, and any subspace should contain 0 as the identity element, right? Yeah. Yes. Yes, exactly. So for a that's what we are going to do now. Okay. So how do we get a basis of a vector space starting with a linearly independent set? So you just gave us a linearly independent set, that is the empty set. By definition, that's linearly independent, right? There is no non-trivial relation among the elements in the empty set. Exactly. So it's vacuously true. There is no element, and therefore there are no relations. Okay, there is no head without a head. Okay. So yeah, how do you start with? So we are starting with some linearly independent set. For example, set that let's take the empty set. Okay, so S is the empty set, and okay, not S is the empty set. We are taking this as an element of, as a linearly independent set. So we are starting with this, say, okay, and suppose you are inside, you are considering a vector space which is finitely generated. Okay, finitely generated vector space. Okay, now since it is empty, so at first it's a finitely generated vector space means what? There is some set S which is generating this, right? Some finite set is generating this. Okay, so that is V is the span of, say, V1 dot Vn. Okay, this may not be a basis, but it is span of some some set with finitely many elements. What do? You append V1 with this, okay, L. So consider L1 as L comma V1. Okay, is this a linearly independent set? Yes, Snowmi? Yes, given that V1 is, so this is linearly independent if V1 is not equal to 0. Okay, that was the right point, because this thing may be 0. It's a generating set, so 0 can be there. We are not claiming that this is a set of linearly independent vectors. Okay. What? No, we are. Yeah. So if we are adjoining to, if we are appending L with V1, so that means it's, well, there were no elements there at all, and you are now taking V1. Okay, and that is a linearly independent set. Okay. Now what you do next? You append one more element from this. Okay, and keep on going. So then repeat the process. That is, then you have L2, which is L1 comma V2. Okay, you append V2 with this. Okay, and continue till you are, if L2 is linearly dependent, you don't have to append V2. Go to the next one. Okay, so there could be two things. If linearly dependent, then consider L3 as just L1 appended with V3. So you are not considering V2 at all. Okay. Otherwise, if linearly independent, that is, if V2 is not in the span of L1, then consider L3 as the span of, sorry, L2 in between as a span of L1 and V2, and proceed. Okay. Do you have a class now? Okay. Are you sure? Okay. Okay. So we should stop here. So we start again in the next class with this one. But the thing that I wanted to tell here is that you can start with any linearly independent set, in particular with the empty set. Apply this algorithm to get a basis. Okay. Because this is a finitely generated set. Sorry, it is a finite set. So at some point, this algorithm will stop. Okay. That's all for today's class. All the best for the exam.